Fine. Sorry. Wrong wire. All right, so where are we in the analysis? Remember that we had this jitter, and it's coming from different source gateways. And we know it depends on the source gateway, and it also depends because that determines the number of hops across the internet, and the more hops, the more jitter. Also, the traffic rate on the remote plate have an effect. Oh, thanks. They affect things. But we don't have measurements of the traffic there, but we do have measurements of the traffic on the link itself. And that traffic will create some amount of the jitter. So we have traffic rates on the link, and we have source gateways. We break up by source gateway, but we have subsets that are still too large. You know, 500 million numbers is just not going to fly within the R environment. You really have to go further. Not if you want to really have a full complement of tools to be able to use, and not if you want to, not if you want to be able to visualize things. You just can't plot up 500 million values. So, and Jeff described to you near exact replicates. That's what we used. And we broke up for each source gateway. We broke up in such a way that we would have near exact replicates of the variable traffic rate on the measured link. And we set it so that there would be 30,000 measurements per subset, about 30,000. Okay, so the number of subsets ranges from, is this correct? Oh, sorry, number of observations. How many subsets? Let's see, on the gateways, it went from one subset to 14,000. Okay, with the near exact replicates. All right, so now remember that we've now switched over. What have we got? We've got this network jitter after having subtracted out the effect of the gateway through this cosinusoid regression that describes the cyclic behavior. We subtract that out, and now we've got what we call network jitter, because that's the jitter that comes from all the queuing on the router. So that's denoted by Q because it's from the queuing, and so that's what we want to analyze. So it's how does Q sub I depend on the traffic rate on the link for the differing source gateways. Now, if you think about it, we take the absolute value. We've got this thing that's varying in a fairly, reasonable way, going plus and minus. And if you looked at it, you might find that it looks like is well approximated by normal distribution, which it does, as a matter of fact, tend to be. As we saw, actually, we have a little bit of stretching of the tails, but not very serious. And then you take the absolute value of that thing. What's going to happen to it? Well, it's going to get very skewed. I mean, it's now nearly a half normal distribution, so it's a skewed distribution. And now we want to analyze this and try to do, we're going to want to take as a function of the rate, we're going to put smooth curves through it. But yet we've got these values sticking way out. Well, this is not a good way to proceed unless we really want to do fairly complex, you say, well, it's half normal. I mean, try some very skewed distribution and we'll do model fitting, but we're going to have to assume a skewed distribution. Well, now you're asking for much harder work. So oftentimes in a situation like this, a remedy is to take a transformation of the data and work with that. And if you need to get back to the original scale, you can always transform back. But you take transformations, like, for example, the log, and you can have a remarkably simpler setting for the analysis of your data. And you find this out, of course, well, in part just by reasoning, we know that if we took the absolute value of these things, we're going to get something that's skewed. We don't need to even look at the data to know that. But oftentimes, it does take looking at the data and saying, whoa, look at that. Now, so log will sometimes work. We can't use log in this case because we actually have 0 jitter occurring. We could add a constant and then take a log, but instead, we took the 5th root because that seemed to do a very nice job of symmetrizing these absolute jitter values. We probably could have found log of a constant plus absolute jitter, but anyway, but this works nicely. And as a matter of fact, we can now proceed with something, rather close to normal. Although, as you'll see, when we do the fitting, we actually use bi-square because we say, well, we're not losing much, even if it is, well approximated by normal. We're still going to do OK. All right, so that itself took a fair bit of study of the data to find out that that worked. So we're continually, fitting things, looking at distributions, and so I'm not going to tell you about that whole process. I'm going to tell you about, having discovered that, what it is that we're going to do. So what we decided was, to start, we're going to use the simple lowest nonparametric regression procedure. Well, that's nonparametric regression is a term used in statistics, over machine learning. It's local learning. Okay. So to estimate, let's see, what is t sub I? Oh, yes, the notation t sub I is just this 5th root of the absolute jitter. All right, so we have kind of a conceptual model here, which is that for each sending gateway, there's t sub I equals f of t sub I plus some random errors. And so what we did was, again, using diagnostic displays, which I'm about to show you, what we determined was that we got quite good fits across the gateways if we took the span, the bandwidth parameter of the lowest procedure to be 0.85, and we used degree 2. We did quite well. And you'll see, again, remember back when I told you about lowest, I told you about, we plot up residuals and we take a look and see if there's anything left. Well, as you'll see, we did that kind of thing. I might mention, just to give you, in doing this, here's another part of the conceptual framework. We're going to do this separately for each gateway. Now you might say, well, what if all the gateways are behaving the same? They're all some nice linear behavior as a function of t sub I. Maybe you can throw away gateway and just pool all of the data. I mean, that would be something, wouldn't it? It's linear across all sites, and they all have the same slope and intercept. Well, we know that's not going to happen. But then you might say, well, OK, they're not going to have the same intercept, but maybe they'll all have the same slope. And then you say, well, maybe they're not linear. Maybe it's curved. What is it? So that's something we need to discover, and that's model building. OK, so we had a set. What we did for the visualization was we selected from each gateway a sample of 100 near exact replicate intervals. So that's 27 times 100, which is 2,700. So any display that we made to visualize the data, we did it 2,700 times. And just put it into, so that we could access each individual site and take a look at it. To assess how we're doing in the modeling. Okay, so that's this sampling scheme. Okay, by gateway now, because that's our and it's a function of traffic rate. So this, shall I say, our representative sample is by gateway, because that's all we have in the way of between subset variables, other than. Oh, let's see. Actually, I forgot to tell you one thing here. Yeah. Sorry. This is all messed up. I'm going too fast. Sorry. This is a function of r sub I, the rate. I mean, I've got t sub I as a function of t sub I. Actually, that's a very nice model. But unfortunately, sorry. Function of r sub I. We needed to get the rate somehow, okay? So, actually, I think I already talked about this. What we did was we went off and we grabbed the multiplex data and we said, let's break time up into 30-second intervals, and then we will find out the rate for each 30-second interval on the measured link. And then we look at the arrival time of each jitter observation, and we say, if you're in interval number 437, then I'm going to give you the rate for the 30-second for the interval of 30 seconds that that arrival time is contained in. And that's how we get the traffic rate. So this should be an R sub I right here. OK? Any questions about this? I hope this is all. OK, so we got the sample. Now, what we discovered was, though, when we were doing this, is that we had 7 of the sites. We discovered this from the plots. But, of course, you could have, if we had known this was going to happen. We just figured, oh, everybody's going to have a huge amount of data. But there were some sending sites that while, they had 30,000 intervals, there were gaps in the traffic rates. That means that there were gaps in time where, those traffic rates were occurring when there wasn't traffic coming from those gateways. So there were big gaps, and we said, well, we don't want to risk fitting things to data where right smack in the middle there's big gaps, because we don't really know what's happening in the big gaps. Especially when you see the results from the other sites, you'll say, yeah, that was a good idea. Now, actually, if we had found out that everything is beautifully linear, then we could have gone back and done it, because we said, well, if it's linear and there's a big gap, that's OK. We've already got our model. So linearity will allow gaps. But if you're doing things locally with LOESS, you say, as you'll find out, that's what we really need to do in the end. So in fact, the 7 never came back. OK. So here's the kind of thing we did. You take the 5th root of the absolute jitter for one subset. So we got 30,000 values here on the display. And we take the lowest curve. Now I'm showing you, this is sort of the final answer, the one that seemed to do a very good job of fitting things. And there it is. This is for Rochester, one near exact replicate subset for Rochester. OK? And here's another reason why we want near exact replicates, because if we're going to fit this curve, we want to each subset, we got to have it spanning. If we were taking random subsets, well, then we'd be back to the same problem that we had to kick, that we had when we kicked out some of the sites. You get a random subset and you say, oh, I can't help but notice that it's all contained within, from 7 megabits to 11 megabits. This particular sample. So anyway, so here it is. So here's the fit to one subset. Here's the fit to another. Whoa, that looks pretty similar, doesn't it? A third, a fourth. I'll be darned. So it turned out as we started looking at these things, we said, oh, these things look remarkably similar within each site. Maybe, well, anyway, I guess after the fact, once you discover something, or if you tell somebody, you say, by the way, we made this amazing discovery, some network engineer, they'll go, well, of course. Naturally, that's what I would have expected. It's better to ask somebody, when you're in this data analytics situation, you say, what do you think these sites will look like? So you don't tell them the answer, you ask them the question first. Anyway, so we were a bit surprised by that. We expected to see much more variability within, when we looked at the graph. So that was already the first hint that we were going to see some pretty substantial regularity from each site. OK, now the next display is, we did this fitting, and we made residual plots, and then we iterated and tried different spans. Now here on this residual plot, remember the span we found was 0.86. So on this plot, here's the residuals from that fit. Here's the plot of the residuals for this one Rochester subset. And what you see is another lowest curve put on that display to see whether or not there's any lack of fit. But that thing has a smaller bandwidth than the one we used to fit it in the first place to see if, do better detection. And the fit seems to be just fine. And that was certainly generally the case. OK, what can go wrong? Lack of fit, never more than minor. no, that's the diagnosis. Never more than minor lack of fit, span and degree lowest, do not need to change. Significant lack of, what could go wrong? Significant lack of fit for certain regions of R sub I. There finally is the correct variable. The rate, action, change the span, the polynomial degree, the robust fitting method. We did use a robust fitting. All right, next display. Oh, sorry, that's supposed to be absolute epsilon I versus R sub I. Clearly I was in a hurry doing this. Okay. All right, so remember we saw this plot last time. This helps check and see whether or not the variability is increasing with the traffic rate. It's increasing ever so slightly, and this is a stable effect. You see this in other sites, but it's so minor we say, you know what, we're just going to forget about it. Now, you might say, what would you have done if you found there was a significant change? Actually, we probably would have gone back and looked for, try to pick a transformation that was even a lower power than a fifth, or maybe gone to log, because that actually, I won't get into it, but that the transformation has an effect also on the stability of that variance. The other thing to do is you can actually just face up to it and say, all right, I have to face up to the fact that the variance is changing as I go to higher traffic rates, and you have to take account of that if you want to get something, you know, that's, shall we say, optimal. But in this kind of exploratory phase, even if we had detected something that maybe you say, well, you know what, we could get better fits if we took account of this, you still just push forward. If this was going to be, if we were on the other side of the house where we had to have this model that really did have to mimic the statistical properties of voice over IP traffic, that part of our analysis, something that was a major deviation we couldn't have ignored. Because we weren't in exploratory mode there. We're in a mode where we're going to be sending synthetic traffic out, and that darn well better just recreate the properties of the data exactly. Here we can be a little looser. But in this case, even for modeling, if we really were seriously modeling this to generate jitter, we certainly would still go with a constant variance because it just isn't changing enough to worry about. Here is a normal probability plot. I wish we had a little more time. I'd tell you the details of this. Maybe many of you know. But anyway, it's a plot where you take the data and you plot it against, you know, the quantiles, the percentiles of the data, the empirical percentiles or quantiles, and plot them against corresponding quantiles of the normal distribution. If all is well, it's a straight line. It should follow that line if it's perfectly normal. It doesn't. It's got tails that are a bit higher than the normal, but again, not enough to worry about. Still, we had robust regression, but that's okay. Least squares would have been just fine. All right. Okay, so we lock our fits. Everything seems working fine. Now we have to start doing recombination. Well, actually, you can say, aren't you already doing it? Well, we have already been doing it. But now, having done these diagnostics and feel assured that we got something that really does represent the behavior of the data, then that was done through 100 samples of each site. Now we start doing things across all subsets. So now we do the full recombination. We're trying to categorize recombination, but it's just so broad in general, it's a little hard to do it. But for the moment, let's try analytic. That's where you recombine by doing a lot of analysis. You have just purely visual. That is, you know, you're sort of looking at the properties of the subsets, and you know, like the barley data. And just studying it, and the display recombines for you. So you might say, well, isn't the visual analytic? You know, I guess it is. I guess we're thinking more for, well, analytic is a broader thing, let's say. I'm not sure. And I'm not sure we even need a taxonomy. But anyway, and some of them are algorithmic. That just simply means, you know, I wanted to fit this lowest curve to each, you know, to each gateway separately, you know, so that I had 20 of them. And I just want one curve in the end. So we do it on all the subsets, and then we're going to average in some way to get a single estimate. So that's an algorithm. It's an algorithm to get the lowest fit to all of the data. Okay, so here's that algorithmic recombination. So we take lowest fits. For each subset, we take means of those fits across subset for each source gateway, and here's the results.
So when you want to sample from this, you iterate, get the lowest and then sample from a normal with that constant variance you picked, or?
We don't sample.
Oh, okay. This isn't the part where you're sampling the, or?
No, this isn't. No, this is not sampling. This is take PSTN. Where's PSTN? It's here somewhere. Oh, there it is. Okay, PSTN is right here. That's the one with 429, well, 14,000 subsets. Okay, there's PSTN. No, the sampling was only done for the lowest fitting. We had to figure out, what should we fit to these data? We didn't know if it was linear, quadratic, exponential, whatever. We had no idea. So we took 100 samples from each site in order to be able to do the model building. The machine is not going to figure this out. I mean, yeah, actually, people have actually tried to, you say you have Y and X, have tried to build automated systems that would find just, I got 50 observations of Y and X, find something that fits, that puts a curve through it. That's too hard a problem, turns out, because so many things can be going on with the data. So we got to, so we do the sample so we can literally see what's going on. We do the fit. But now, for PSTN, we had a sample of 100 we based it on, but we actually have 14,000 samples from PSTN. Sorry, 14,000 subsets. I used the wrong word. 14,000 subsets altogether. We average across all those subsets. We take the lowest fits and average across all subsets for PSTN. Is this clear? Because this is critical. Okay, we had 14,000, but we did the model building to figure out lowest with 0.85 through those 100 samples and visualizing those. Okay? All right, any questions about this, or?
All those variations to see if there is those based on just differences in the hardware they have for locations or the routing policies, because there's some pretty different things.
There are, but these things, all right, now you say, oh, I mean, is this just, is this, where's the confidence intervals? Oh, the confidence intervals are all there, sort of. If we computed confidence intervals doing the, following the statistics thing, I mean, we have really a tremendous amount of data here. In fact, well, I'm going to show you something in a minute. We knew from looking at the plots that these patterns were almost visually they were almost absolutely identical when we plotted things up with 100 samples. So that's really, we're locked in on what that thing was. Now, what's causing it? Well, there just is going to be different experiences coming from, there'll be an experience base from Buenos Aires. It's going to be changing through time, and it's got, it's gotten certain, or time of day. It's got certain characteristics to it. So it's the Buenos Aires, trip across the internet that's producing this. But is it reproducible with these data? Absolutely. So, in fact, as a matter of fact, if you take a look at this, let's take a look at this. For each one of these lowest fits of, say, in the case of PSTN, for the 14,000 fits, we're going to actually take the fitted values and evaluate them at some equally spaced set of points along the rate axis, and then just take the mean of those. So you do that for every single subset. So for PSTN, we're going to have a mean of 14,000 values for each subset. And then what we do is we make box plots. And here they are. So we took the mean of these subsets. And what you notice is the variability of the means within a site is, I mean, these are, we're seeing all the, the limits of the data here. So what this says is that, this is sort of verifying what we saw with our eyes, namely that those curves, those 14,000 near exact replicate subsets are producing lowest curves that really are, this is reinforcing what we saw with our eyes. Because the means are varying by an extraordinarily small amount. Furthermore, we're seeing if we take those means and make normal probability plots, they're varying across the subsets of each case, of each gateway, by normal distribution. So that taking the mean to get back to the one single lowest fit, that seems like a reasonable thing. We did the same thing for, evaluate the curve at 9 megabits per second and look at how it's varying at 9 megabits per second across subsets, everything, and everything is very tight, like you just saw. Now, honestly, what does that mean when we're all done? What that really means is we had way more data than we needed for this part of the analysis anyway. I mean, for this part, it's sort of overkill. Now, for the actual modeling of the, of the individual connections, well, it certainly was not overkill. But for this jitter analysis, we have a vast amount, way more information. We could have done with, 1,000th the amount of data and still understood the behaviors quite well because of this regularity going on in the data. All right, so this is just plots other things. There's the standard deviations, also quite stable. The one thing, let's go back here, because this is sort of the payoff here, right here. This thing is the payoff. This is the thing to look at, because you say, well, OK, we've actually ordered this by what? Whoa. Oh, yes. We actually ordered this by the mean of the means. You just take all the fitted value, you take, well, this is basically the mean of the jitter, but you take all the means of the subsets and then take the means of those. Here's the order. So it's sort of like, overall the lowest amount of jitter up to the very highest. And if you take a look at that, actually there are some surprises. Up at the top, you see, most of the top things are places in other countries, except, there's Copenhagen and Frankfurt and Milan and Buenos Aires and whatnot. Although right smack in the middle of that is Tampa. OK, well, this is just distance. I mean, what really matters is internet distance, and we don't know what that is. And then you come down and you look at this and you say, oh, what's the PSTN doing there? That was supposed to be down at the bottom. Why is that there? We have no idea whatsoever. OK, it's unclear. So, but in general, the overall, there are some anomalies sticking out here, but again, this is about internet distance and what's happening on some of these devices individually. But still, it's confirming. It says, OK, fine. We know there's going to be some anomalies here, but you know what? This is all behaving the way we would expect, so, and because of the rates and so forth and so on, we've been able to verify to just about anybody's satisfaction we've talked to that, yes, this is very close to the offered load, and everything seems to be going about what we would expect. And it looks like all your measurements are very, very accurate, and so everybody's happy in this part of the analysis. OK? OK, actually, this is Jeff's slides. OK. All right, so I'm done. I'm done. OK, you want to say a word or two about the computing?
I don't know, maybe time for a break. You want to take?
Well, we're finished.
All right.
I think this is our last lecture. All right, you want to, I mean, I could,
What do you want me to say? Do you want me to run through what I showed you?
that'd be good. How long will it take?
10 minutes.
Okay. Okay, that's good. Yeah, let's do it. I mean, well, we don't just, we get back to the Hadoop stuff. Anybody want to throw that around, or you got questions, or?
Yes.
Can I ask about the normal plot? Do you remember that service?
Yes, which one?
Just this slide back, you had,
Of the means?
you had one normal plot for each gateway pattern.
Yes.
Each one of those dots represents one of the subsets, the mean from one of the subsets?
Yes, the mean of the jitter curve. You know, let's say the integral. You know what I mean?
Ignoring what was your independent variable? What was your
It's traffic rate. Yeah.
ignoring traffic rate?
Well, you're averaging across traffic rate. So I have a curve here. I have a curve like this, say Frankfurt, and Frankfurt, for one of its subsets, I have a lowest curve. And so I evaluate that curve over a grid, and then I just take the mean of all those evaluations. So it's an average across all the rates.
So then I'm a little bit confused about what we're looking for in that plot, because don't we know just from the central limit theorem that the means are going to be normally distributed? What are we looking for?
Well, yeah, you would hope that would be the case because of the substantial amount of data. But it's not normal until it's normal. And it's not normal until you demonstrate it's normal. No, you know, we get the right to hope because of the central limit theorem, for sure. Absolutely. Absolutely. But again, you know, any metaphor that you want to pick, it applies here. You know, I'm from Missouri. You got to show me, you know, whatever. So that'll be the final exam. Everybody's got to have a metaphor for this. Okay. So, yeah. I mean, good point. You know, I appreciate that. So there's a lot of things that we hope for here in the analysis we expect to see, and we did. You know, but again, it's not happening until it's happening. It's not the offered load until we demonstrate it's the offered load. Okay. Go.
Any questions about Hadoop?
Oops, I got to get out of your way.
Are you sure the best thing to do is to just break it off and start on time, I think?
What do you mean? You want to?
I mean, by the time I get them,
Oh, you mean because somebody else is coming?
somebody else starts it too.
Yeah. Okay, I'll tell you what. Let's do this. Does anybody have any questions about the? Yeah. Does anybody have any questions about the Hadoop, the FreePay? You know, what's it like to program in it? How do you get a copy?
I have a question. Is the gentleman here that, so there was this issue of MapReduce, and MapReduce has a specific flow. And then on the first day that somebody said, have you heard of this other technology that talks about arbitrary flows of data? And
Ricardo?
No, it wasn't Hadoop at all.
Oh, I see.
It's a
Okay.
separate technology. And then I realized when I was walking, this is really interesting to me. So that person here, because I'd like to know the name again. No, that person's not here. That's a shame, because I wanted to investigate that.
All right. Well, spread the word. You know, Jeremiah's after somebody. He doesn't know who it is, though. So actually, you can send it. Get a hold of Vishy. You can send an email to everybody.
Because I think it's very forward-looking.
Yeah. Sure.
MapReduce has sort of one flow, and what he was talking about was the capacity to basically do arbitrary branching, arbitrary number of steps. And then
Yeah. Okay. Yeah.
I have a question. Suppose now we have thousands of computers, which
Yeah.
Each one has, for example, 1 gigabyte memory. And these thousands of computers are connected by internet. Can we build some general environment so that it can run program which require 4 gigabyte memory?
You know, that's part of the beauty of all this. It really does scale to that kind of thing. And of course, that's not, I mean, that's a lot more, that's Hadoop more than us. However, from the data analysis point of view, what it would mean is you've got to get, you know, we picked subsets with 30,000 observations. You would be trying to make your individual subset computations even smaller. If you're, the more limited your memory. As a matter of fact, overall, what you really do want to do in general is, even if you have even if you have 128 gigabytes to deal with, you still nevertheless want to get small, because there's a whole lot of reasons, not the least of which is that makes it easier to share. You know, we've been worrying a lot about, we've suffered deeply actually, is what's happened is because we're working with ITAP on a cluster that will, where we said we got to design for this kind of parallel computing with data, because they have this, campuses across the whole country, across the whole world, they have these high performance computing clusters, but these are for people running massive simulations that are massively parallel. And what it is like the TeraGrid, it goes across the whole country. They're running batch jobs. It's like, submitting card decks. That's what it's like. And so the architecture of those environments, by architecture I mean the way things are scheduled and things like that, and what they do about disk and things like that, useless for data analysis, absolutely useless. So we're working with them to develop an environment. Now, the nice thing about that is that we can get Hadoop to do the scheduling. But it works a lot better if everybody's, when you submit your 14 million parallel computations to do, it's better if each one of those is small, because if somebody else comes in and wants to use it, then that person gets processors as your little job ends. Now, we're working to see about scheduling where if you happen to do something that takes a long time, that we can interrupt that. So we're in the middle of exploring that. So, but this all scales like that. We're just waiting for the GPUs. We can't wait, because more processors, this is even better. Okay, so.
A follow-up question is that if it's possible, then can we build something like P2P? I mean, everybody can connect, and since for each computer we couldn't run a program that requires 4 gigabytes because each notebook only has 1 gigabyte memory. Then, if we then connect with each other, then everyone seems like have a very powerful server.
Yes.
Do you think it's possible?
Well, I mean, yeah. Go ahead, Jeremiah. Why, let's.
Technical limitations right now with Hadoop. It basically, I glanced over the fact that it has a central name node and a central taskmaster. So it isn't this sort of distributed solution that you're talking about there, where you can arbitrarily scale it up to a peer-to-peer solution.
Yes, I mean, we can build
Well,
It's an interesting idea, but it's well outside of the technology that we're working with.
Well, if you want to, yeah, but I mean, after all,
Hadoop maxes out at about 4,000 nodes. And
Oh, does it? I see.
Facebook is trying to address, Facebook and Yahoo are trying to address those limits.
Right, right.
That's what I mean by it has one name node. That limitation comes from having one server processing all the data requests.
I see. Well, it's just a question of time then, I guess. So, okay, so the immediate Hadoop, I guess, so Jeremiah is saying not. But are the principles that we put out here going to work in that, subject to it being more fully peer-to-peer? Sure. We just need to see what we're doing is we're exploiting distributed computing systems to do data analysis. We're up sort of a level up here, and we grab what we can to put underneath. Okay? So anyway, good question. Let me do this. I'd like to shift over to something a little bit different. It's sort of a kind of a summary of sorts, except it's going to be the big summary. So anyway, so here's one question for you. When did machine learning start up? As it has become now. I mean, when was it? When did it start up? What's the history?
data collection.
Sorry?
Data collection.
No, machine learning. Like, what? Actually, when was the name first used? CMU, 80s. What's that? Where?
I guess I'm thinking back to like Blumenhart and back when he was doing perceptron type stuff.
Yeah, perceptrons, all that stuff. So, oh, is that when that was? Right. Yeah. Okay. So what was going on in that current of well, I mean, I suppose you could say it was both. I mean, I don't know if chess programs are, I guess they're part of machine learning too. I mean, there's a whole lot of things going on. But suddenly in computer science, there was this notion, well, listen, we just want to build algorithms to do things with data. And yeah, it's nice that there's this field of statistics, but we don't care about probabilistic inductive inference. We're not going to search around for statistical models. We're going to, we're just going to take algorithms and try to treat the data as, based on, judgments of, what the data are like and things like that. So, and of course that grew and grew, and here you all are now, and that's still an important conceptual framework. And of course there's now a lot of, probabilistic stuff in the field of machine learning. But the thing to appreciate is that actually the same thing was going on in statistics, that one day, actually most of this was the result of John Tukey, who started saying, what the words he used was, we need exploratory as well as confirmatory. So what he was saying was, well, it's fine. We've got all these statistical models, but you really need to be able to explore the data. And there's two things. You need to be able to have things that fit to the data and that don't necessarily derive from some specific model. They need to be rather general, like the Loess procedure, for example. It needs to be general, and it needs to accommodate very, very wide scope of data, so that when you're getting in there and taking a look at the data, you have these algorithms that are operating on the data, doing good things to let you figure out what's going on. And then maybe from that, you will wind up being able to see what's going on. At the same time, he was saying, in fact, he's got a book. He published a book, Exploratory Data Analysis, which was doing that. It's sort of about analyzing data, and there isn't a single model in it. There isn't a single statement about this is distributed like this, but rather it was using it was using algorithmic methods, and at the same time it was also using visualization. At the same time, Tukey was saying, we've got to visualize the data as part of this process. So all of a sudden, together is the visualization, and what I think is fair to say is machine learning. It was like the startup of machine learning when itself, so you might say, well, how do I know something is machine learning? Well, it's because some statistician says, where's the model? There's no model here. How can you analyze data without a model? So what I'm really getting at here is that, and of course, we do need probabilistic models for data. It's not as if we don't need that. I mean, that certainly is needed. So you might say that there is a conjunction of three things that really are desperately needed if you want to treat data that are in a way that gets from them the most information possible. And the three things are algorithmic numeric methods, like you see, a very large number of in machine learning, and that also exist over in the field of statistics. You need stochastic models. You need to be able to make inferences from those stochastic models. So that's sort of, in a lot of cases, not all cases. By the way, we don't need to do any statistical inference with these data. Okay, that's another thing that's happening with large amounts of data. A lot of statistical inference issues that come up with smaller amounts of data, or even for some big data, they certainly didn't obtain in this case. We didn't have to worry about statistical, variability of our estimators because we had a lot of data and we really had it nailed. But we did need the probabilistic modeling. We absolutely need that. So anyway, so we got algorithms for data, we got probabilistic modeling, and we got visualization. three essential components if you want to get your hands around data. So I would encourage all of you to become knowledgeable about all three things. It's interesting in computer science because there is actually a computer science visualization community. It's not just computers. Well, a lot of people are in computer science. They're also in engineering departments. So they're doing data visualization. Maybe you're aware of this, maybe you're not. There's Viz Week that occurs every year, and people show up in droves from electrical engineering and computer science and other related fields. And then there's a machine learning field, but I don't see too much visualization in the machine learning field, and I don't see too much machine learning in the visualization field in computer science. So interesting phenomenon. Maybe I should have a joint conference one of these days. Anyway, so that's sort of a summation, but I say this because in tackling divide and recombine, that we set as a premise, that we need to be able to do all these things, and we want to preserve this for large amounts of data.
I have a question.
Okay, sure.
So you've been at Purdue for a very long time. Do you
Well, okay, yeah.
Machine learning is basically when you look at university machine learning, you do a collaborative group of computer scientists and statisticians within those departments. Do you ever see it being its own department in the future?
Machine learning being its own department?
Yes. Instead of embedded in statistics and computer science.
Well,
Is that the sort of thing that happens in the, because I know when I went to Utah State University, statistics was still in mathematics. And there was this whole should statistics be separate from mathematics that happened basically 20 years ago. Is that sort of thing going on?
you got an answer?
So it does seem like there's a little trend there that people are starting to differentiate.
Well, I think here's the problem. Look, the best way to look at it, this is the way I look at it. They're the same field. The goals are exactly the same. If you look at what's going on, and when people get data in machine learning, when people get data in statistics, you're really after the same thing, pretty much. So I think, and if you look, and machine learning has migrated. There's just a lot more statistics within machine learning than there was before. I've been to some of the major conferences, so yeah.
See, that's what's going on here.
Well, sorry, I didn't catch that. It's what?
It's just its own very large multiple.
It's a department at CMU?
Oh,
I see.
there's one. There
Okay.
is one department. We know there's one.
Okay. Well, the name doesn't matter. Actually, the people in statistics at CMU are very heavily involved in machine learning. So, look, forget departments. Okay, it actually doesn't matter. What matters is the intellectual content of the disciplines. If you go to NIPS, you're going to see, we've hired faculty out of computer science for the statistics department, and when they give their talks, you say, I can't tell what department this person is in. It's not possible. So it's really the intellectual. Universities have organizational things that they lead a very irrational life of their own. So, but I'm going to say the intellectual content is really, you have different backgrounds of people and different skill sets. I will say that certainly, but that's okay. That's great. I think the hybrid that's come out of machine learning and statistics together it's marvelous. It's great. It's been a great thing for the field of data analytics. Let's put it that way. So, and it's fun to see it happening. And I hang out in all three fields: visualization, machine learning, and statistics, because I think they're all important for analyzing data. So I want to know about all three. Okay, that was a good question. Oh, I like that. Anything else? Any technical questions? Any thoughts? All right. Well, thanks for coming. Nice having you here. And I hope it's been overall a positive experience and you're learning a lot of stuff and you'll go back energized and start tackling problems having to do with data. Okay?